In this problem, let's try that again. Whoops. Right about there. Oops. Come on. Alright, here we go. Well, it looks like Billy has some money in the bank. Billy said that his bank pays continuously compounded interest. And he says that he put $100 in the account exactly 9 years ago, and it has grown to the amount of $220. Question is, when will he have $300? These problems are driven by a mathematical relationship that is well known. It's exponential growth, and in general there are two forms that this can follow. A equals, what happened there? Alright, let's start all over. Alright. Well, it looks like Billy has some money in the bank. About exactly 9 years ago, Billy put $100 in the bank, and he now has $220. Billy has some money in the bank. He put $100 in an account exactly 9 years ago, and he now has $220. The bank pays continuously compounded interest, and Billy's question is, when will he have $300? All right. Now, there are two formulas that come up in a problem like this, but they're related. If you have M compounding periods per year in your bank account, so if it's quarterly or monthly or daily, where M is the number of times per year, then the amount in there at any time will be the principal times 1 plus the rate that you're getting divided by the number of compounding periods raised to the M times T, where T is the number of years. This is the formula you would use if M is any finite value, so I'll write less than infinity. If M is equal to infinity, then we say that the interest is compounded continuously, and this formula becomes one of this form. It's kind of interesting to see how this happens. As M goes to infinity, the quantity 1 plus r over m to the m, just that piece, becomes e to the r. So it's still an exponential problem, but it now follows a somewhat simpler to look at formula. All right. So again, P is the initial amount, A is the amount it becomes, R is the rate, and T is the amount of time in years between the principal and the accumulated amount. So in this problem, this is the formula we're going to use. And there are a couple of pieces to this. This hint gives us a suggestion, but hopefully we don't need that hint to realize this. If I know two values that he has in the account, $100, $220, and I know the time involved in between the two, then staring at this formula, the only value I would not know is the value r. So I can solve for r by plugging in everything I know and solving for the one unknown. So the amount I'll have get out is 220. The amount I'll put in is 100. The time that it's in there is 9. So this is r times 9, and I can now solve this for r. Now we're down to an algebra problem. The idea here is divide off the 100 to isolate the exponential first. So if I divide both sides by 100, I'll get 2.2 on the left. I'll get an e to the 9r on the right. And now I'll use a logarithm to knock the exponent down out of the exponential. And since the base of the exponential is the natural log, and since my calculator knows how to calculate natural logs, I'll use the natural log. Natural log of e to the 9r is just 9r. So the rate he's getting must be, solving for r here, dividing by that 9, natural log of 2.2 divided by 9. And the value for that turns out to be, and you don't want to round here, every decimal place is important on the growth rate, or the interest rate in this case. So I'll put 4 decimal places, 0.0876. And I now know one of the missing pieces to my formula. A is P e to the 0.0876t. And I can now use this form to finally answer Billy's question. He wants to know when will he have 300. So he's got 300 that he wants to come out, and he's leaving it in there for some period of time that we're trying to determine. So we're going to want to solve for t. But notice I haven't put in the principal amount here, and we do have to take a little bit of care in selecting this. We can use either the 100 we used before, or we can use the 220 that Billy has in there now. Either will work, but we will get naturally a different answer for either approach. So we got to understand how those two answers differ. The time that is measured here is the amount of time between these two numbers, the number I haven't put in yet and the number 300. So if I put in the number 100, that would be talking about the time it took for the 100 to grow up to be $300. So the value for t there would include the 9 years that it took the money to grow up to be 220. And as long as I understand that, I can work with it. So I can place 100 in here and get my value for t out and then interpret it properly. If I put 220 in, and I'll do that just because it's the example I haven't discussed yet, then the time I'll get out of here will be the value, the amount of time it takes the 220 to grow up to $300. So that would be measuring time from right now. How much longer will Billy need to leave the money in there? Solving this problem is virtually identical to finding the value of r. It's a variable up in my exponent, so the first thing I'll do is isolate the exponent.